So this is the chapter or topic that comes immediately after the divide and conquer approach. So you will see the sorting problem is quite related to the divide and conquer approach. When we introduce first of all, the very first two examples are sorting algorithms, the insertion sorts and the merge sorts. And among these two algorithms, merge sorts is the divide and conquer, is an example for divide and conquer approach. And now in this chapter, we're gonna basically look at three main types of sorting algorithm. First, quicksort, and then heap sorts, and the last type of sorting algorithm is linear time sorting algorithms. Okay, so the quicksort is a typical divide and conquer approach, but heap sort is not. Heap sort is a algorithm that relies on some data structure called heap. Okay, so we will see that each of them have very specific advantages and disadvantages. And the third type, as the name indicates, it's a sorting algorithm that runs at linear time, which seems incredible, right? Because we know the merge sort seems to be the best one so far we have seen, which runs at n times logarithm of n. Then how come it could be a sorting algorithm that has linear running time? Well, it is approachable only with some constraints on the inputs. So it shouldn't be any type of inputs that can generally have a linear time running time running time efficiency, which is not practical, which is not doable. But if we place some constraints on the inputs, say the inputs elements are within some regions or any kind of other constraints, we can achieve these very efficient linear time efficiency. Okay, so today we will first talk about quicksort. So the worst case for quicksorts is n square, big zeta of n square. And the average case is big zeta of n times logarithm of n. And also it has very small constant factors, which means when the when the n input size is small, it will also already show some advantages over, for example, insertion sort. Okay, and it's sorting in place, doesn't require any additional memory space. Okay, so it's a typical divide and conquer algorithm. Okay, and there are basically three steps in order to sort such a sub-array. Okay, so let me use a different color here. So it's the array A, that from index P to index R, that need to be, this segment of A need to be sorted. Okay. The divide and conquer. So we can actually make a comparison between quicksort and merge sort. Okay, the main difference is in the dividing step. Okay, recall the merge sorts. How do we do the divide? Right, it's simply to compute the midpoint. We take the first the index of the first elements and the last elements. We'll compute where p plus q divided by 2 where the midpoint is, or rounded to floor, right? That is the midpoint. But it looks like quicksort uses a different way to in the divide step. Okay, so it's some new procedure called a partition procedure that we need to implement. Okay, so it's a process that's rearrange the array. Okay, and we need to rearray it into two sub-arrays. Okay, which is from P to Q minus 1, that is the first segment, the first half, and from Q plus 1 to R, that is the second half. And there's one element left in the middle, right? That is a AQ left. So that AQ is the pivot. Okay, AQ in the middle is the one to split the two segments. And we need to have such a condition satisfied. All the elements in the left from P to Q minus 1 should smaller than AQ, should smaller than the pivot. And everything on the right within Q plus 1 to R should be greater than or equal to AQ. Okay, so this is more complex, a more complex division than merge sort, right? Merge sort simply computes the immediate points, immediate midpoints, and doesn't do anything sophisticated, right? But in the quicksort, we need, when we do the division, we already make some arrangement. We already make some useful arrangement by make sure that everything on the left is smaller than the pivots and everything on the right is greater than the pivot. Okay, so which is some additional cost. Okay, so this step is not a constant running time operation. Okay, so finding the index Q is a key operation, right? And after we have done the division, the next step is to conquer, right? We simply use the recursive calls to the two sub-arrays, right? We have P to Q minus 1 and the Q plus 1 to R, right? And actually, after the conquer step is done, we are pretty much done with the algorithm because no work is needed to combine the sub-arrays because they are already sorted. They are sorted in place. We don't need to merge them into, we don't need to copy back from some additional memory space like what we did for the merge sorts. Okay, so after the conquer step, the entire array is now sorted. Okay, all right, so let's look at the details regarding the partition step. Okay, all right, that's what we get for the quicksort procedure. Okay, it's a really neat code. Okay, the quicksort procedure defined on 3 arguments: inputs, starting index P and R, right? Yeah, so quicksort over, we usually that is a good question. So usually speaking, merge sort comes with additional memory space. And if we are sorting something on a large server, a lot of data to be sorted, then without considering the memory cost, that is a very dangerous operation. So, but quicksorts also has its own disadvantage because it's a recursive algorithm, and we don't know what would happen to the stack of the memory if there are too many recursive calls. So I would say that, to put it simple, I think quicksort can be sometimes preferred in more cases. In different programming languages, I think, for example, in Python, the sorting algorithm is some variants of quicksorts. It's called team sort, but it's some more detailed implementations that are different from quicksorts. But because it's an in-place sorting algorithm, so it is. I think it is preferred in more cases. Yeah. So it's a quite neat implementation in this case, right? We just need to compute the. We first need to. Of course, we need to check whether this is the base case, right? If there's only one element in it, we don't need to sort anything. If it's the if it's the non-basic case, we need to call the partition procedure. Okay, and we have designed a partition procedure in such a way that the pivots index Q will be returned. Okay, and then we run quicksort, call quicksort twice on each partition recursively. Okay, so really we can see that the key is how we implement the partition step, right? So we need to make such a procedure that it can basically separates all the elements in the array into two groups, one in the smaller group and the larger group. Okay. All right. So let's look at the partition procedure here. Okay. It also takes the inputs A, P, and R as inputs. So what it does is to take the last elements, because R is the ending index. It copies the last element into X, which is the pivots of comparison. Okay, and it's initialized the first counter, I counter, to P minus 1, which is the one to the left of the starting index. Okay, and also the second loop, the second counter J, is from P to R minus 1. R minus 1 means that we are excluding the pivots because the last element is used as the pivot for comparison. So in the for loop, we don't need to compare to the pivot with itself. So we need to just exclude it in the for loop. All right. So in each step of the for loop, we're comparing the elements with the pivots. Okay. So if the element is smaller than the pivots, we need to increment the first counter I by 1, and then we exchange AI with AJ, okay? Because we want to switch the smaller elements, AJ, to the front, right? We want to swap AJ and AS so that the smaller elements to the front and a larger element to the back. And the last step is to exchange the current AI plus 1 with the pivot so that the pivot is moved to the middle. Okay, and finally we'll return I plus 1 as the index for the pivot elements. All right, so we'll show an example of how the algorithm runs. Okay, so because initially the elements look like this, the last element is 4. We are comparing the first element 2 with 4, right? Which means 2 is smaller than the pivots, and we need to exchange AI with AJ. But in this case, I plus 1 is the same value as J, so we are actually exchanging the same elements, which means we don't need to do anything. And in the second, in the third iteration, and the AJ becomes 8, and 8 is bigger than 4, so we don't need to do anything, right? And 7 is also larger than 4, which means nothing needs to be done until we've got 1, until we got the AJ equals 1 here, right? Then in this case, AJ is 1. It's smaller than the pivots, so we need to increment I by 1, which means I points to the 8 here, and the AI and AJ will be exchanged, which means the larger element 8 will be to the new position here, 8, and 1 will be exchanged to the position of I here. Okay, so that's how the smaller elements at the back will be moved towards the front. Okay, and the smaller elements are moved back towards the end. Okay, all right. So that is the first couple of iterations, and after the whole step is done, okay, let's look at the last operation. So this is the last iteration where the loop is done, right? After the loop is done, the J ends here. J ends at the R minus 1. So the last step at line 7 will copy the pivots to the middle by exchanging the 4 to the middle and the 8 to the last, so that now we have the whole sequence partitioned, and it's actually 2 parts. The leftmost is the left half is the ones that are smaller than the pivots, and the right ones are the elements that are greater than the pivots. So that is how we decide. That is how we design the procedures for partition. Okay. So the thing is that now we can kind of guess how much running time it will need, right? So nothing too fancy here because it's just a for loop, right? It's a for loop with a combination of if statements. So it's basically a linear comparisons that we are making, right? We need to go through all elements linearly. Okay, so the trickier part is how do we analyze the average case versus the worst case. All right, so first let's look at how correct the algorithm is. The partition procedure basically selects the last elements as the pivots, and we basically partition the array into 4 parts, right? The shallow, the light gray area are those smaller than the pivots. The dark gray area are those greater than the pivots. The white areas are those we haven't scanned yet, right? And the last area is the pivot itself. Okay, so since the algorithm, so these texts are about how we use the loop invariant to analyze the algorithm is correct. So which is not required from this course. If you're interested, you can read it on textbook. Okay, so I will skip this slide quickly. All right, let's skip the loop invariance. All right, so the time is what we are interested here. Like how much time we need to do. As we said, it's basically a very simple linear, a simple for loop implementation. And it makes sense to say that the algorithm runs in linear time. I mean, the partition procedure runs in linear time, described by big theta of n, right? Because it uses only one for loop that iterates from p to r minus 1, right? And altogether, when we put the partition at this step, take into the consideration for the partition cost, we can start analyze the running time for Quicksort. So yeah, we're pretty much done today. So I will leave the full analysis for Quicksort's running time to the next lecture on Thursday. So I see a question that I haven't for assigning text read. No, I haven't assigned any text readings here. So I think basically the contents in the slides are sufficient for you to do the assignment questions. But if you are interested about more details, that textbook is a really good one. You can you are encouraged to read any chapters related. All right, let me stop recording for now.